Hi, good morning, everyone. Excuse me. All right. So today we're going to finish up the review of 3260. Should be able to get through it today, and then we'll start into electromechanical machines on Friday. So I believe where you left off on Monday's class is looking at the frequency response. So I want to briefly review that really quick. The main idea is that if you have a linear system, which you can describe by a transfer function, it is a property of a linear system that if you put in a sine wave, you get out a sine wave. And the important things to know about this is it transforms two things about this sine wave or cosine wave. One is it scales the magnitude of that sine wave. So looking at what I mean by this is that it scales the magnitude that the input is defined by a sum of cosine waves or sine wave, doesn't matter. But say we have a cosine wave, it has an amplitude associated with it, given by this coefficient A sub k out front. It has a frequency, and I think there's a small error in the notes. This is missing time right here. It has a frequency of omega sub k, and it can have a phase angle of phi of k. The output of the system, so it comes out at steady state, is equal to this amplitude scaled, and scaled by this magnitude of this transfer function evaluated at I omega k. This is what we often call magnitude. The frequency passes directly through. So if you put a sine wave in of 5 hertz, you're going to get a sine wave of 5 hertz as well. Right. The phase of that input passes through, but also you then have a modification of the phase angle given by the phase of that transfer function evaluated at that frequency. This is then phase. Okay. So this is just a really basic relationship of linear systems. How we plot this information in terms of magnitude and phase is what we call a Bode plot. Right? So this should be definitely review. Hendrik Bode, the namesake of the Bode plot. Where did this individual go to undergrad? People know this? Ohio State University, right? So he grew up in Urbana-Champaign, Illinois, and he wanted to go to Urbana-Champaign at the age of 14, and Urbana-Champaign said no, and Ohio State said, come on in. And then so he got his undergrad degree in math at Ohio State, PhD in math at Princeton, and then went on to become one of the most famous controls individuals in terms of control systems. So there's one of the most prestigious awards in control systems is called the Bode Award, named after him. So a very important person in controls field. If you decide to go to graduate school in controls, you'll see his name everywhere. A lot of things in terms of how we understand control systems were invented by him. The first being the Bode plot. This is a pretty fundamental tool that we use in control systems integration, etc. So to kind of work with this a little bit, we're going to look at example 3.8. And so the main thing here is that a Bode plot describes how the magnitude and phase of a transfer function change as a function of frequency. And this is an example. This is coming directly from a spec sheet for an op-amp. So something you would have learned about in your electrical circuits class. So the purpose of what this op-amp was supposed to do is it's a pretty simple function. Is if you have an input voltage into this op-amp, Vi of t, the purpose of this op-amp is to multiply Vi by -2, and that becomes your output. Okay, so basically voltage in, the op-amp performs a function, right? It multiplies this by -2, it flips the sign, and then scales it by 2, and that's what it's supposed to do. Okay, that's the main function of it. Now this is its idealized function. In a spec sheet with the Bode plot will show you actually how it will really function based off of an experiment. So the question is then, say for instance, I were to put in a voltage into this op-amp of 0.5 volts plus then a cosine wave with a frequency of 400 megahertz. Right? So this would be 2 pi times 400 times 10 to the 6 t. And the question is, what is V? Oh, okay. So if this was working in an ideal fashion, it would just be -2 times this, right? But if you look at the spec sheet for this op amp, this is an analog devices op amp. It shows a little schematic, and then I'm cutting out a lot of the spec sheet and just showing the Bode plot portion of this. It has this spec sheet given here. All right, so this is, it doesn't call this a Bode plot in the spec sheet, but it is. Okay, so it provides a frequency versus gain or amplitude in decibels chart for you. And it doesn't actually provide the phase information. I figured this out from the spec sheet in terms of what the phase should look like. But then it gives them this phase information for the system. Okay. All right. So the question is, given this voltage, then we want to know, given this voltage signal, we want to know what the output is and whether or not it's performing this idealized function of just multiplying that signal by -2. Okay. So going back to this. Okay, so here is VI, right? And what we know from linear systems is that it's going to follow this relationship. As the input, or a little bit above this in the notes, we said that this is our generic variable for the input. This is our generic variable for the output. And we say it's going to, any linear system is going to perform this function in terms of scaling the magnitude, shifting the phase, right? So then the question is, what is V out going to be for this problem? I should open my notes for this. Okay, and so given this signal here, we have, if we want to start to tabulate these, if we look at, we can break this up into two different parts. So one doesn't look like a cosine wave, but we'll talk about why this is a cosine wave in a second. The other one obviously looks like a cosine wave here. So if we were to write ourselves a little table to try and understand what's going on here, we have a two-term summation, right? So k goes from 1 to 2 because we have two terms here. So we can write ourselves a table here which says this is what k equals omega k, ak, phi k, and then we're going to pull some things off the Bode plot. So the magnitude in decibels, the magnitude not in decibels, we have to do a transformation, and then we're going to find the phase. Okay. All right, so the very first term is 0.5. Okay. What is the phase of just a DC voltage of 0.5? Or sorry, what's the frequency of a DC voltage of 0.5? So I heard 0 from somewhere in this region. 0? Okay, so why is it 0? Yeah, so it's not oscillating. If we were looking at what is the plot for 0.5, time is just being held at 0.5. Okay, so another way to look at this, so we can say that 0.5 is equal to 0.5 times cosine 0 t, right? That'd be another way to look at this, right? So cosine of 0 is 1. Right, so multiplying by cosine 0t is doing nothing, right? It's not changing at all. Okay, so anytime you see a DC term, that's just a frequency of 0. Right? Okay, so we'd say that for the first term, our frequency is 0. Our amplitude, right, is just the amplitude of this cosine wave, which is 0.5. Phase, there's nothing here, no phase shift. This is 0 as well. Okay. Next term, if we look at here, this is cosine of 2 pi times 400 times 10 to the 6, or 400 megahertz. All right, so this is 400 megahertz. Amplitude, 1. phase 0. All right. Any question about reading the voltage signal and understanding the different components of it? Okay. All right, so now on to the Bode plot. So the rest of this we have to fill in from the plot. So first we're going to look at what is at a frequency of 0, what is the magnitude in decibels? Okay. So a frequency of 0 does not exist on a Bode plot, right? So a Bode plot is given a log scale. So that would be then 10 to the negative infinity. That doesn't exist. But we know from your work in hand plotting Bode plots that they asymptotically, if they're off the chart, you just take the asymptote and keep on going, right? So in this case, a frequency of 0 is way, way, way over here, all the way, let's say all the way in Worthington, North Columbus. So we're just going to assume that this is flatlined here, and it's going to continue on and being at 6 decibels, right? That's how we would read this. So we'd fill in here, and we say that the magnitude in decibels is 6. Right. If we want to then convert magnitude in decibels to regular magnitude, remember that this is our transformation for going between decibels and regular magnitude. Or if we want to solve for regular magnitude, if we happen to have magnitude in decibels, it's this right here. Okay. So I'll save you the effort on this one. If we were to do this conversion, a magnitude of 6 in decibels converts to a regular magnitude of 2. Okay. Any questions on that? Okay. Okay, the next frequency is 400 megahertz. So I'll zoom in here a little bit. All right, so what is the magnitude or gain of the system at 400 megahertz? Yes. Sorry? 3. Right. Okay. So just a reminder on how to use a Bode plot, right? So this is 100 megahertz. Next line is 200, 300, 400, right? So you go, this would be 400. Go up to where this intersects the plot, and then you see that this is a gain of 3 decibels. All right, 3. If you would do this conversion again to get back to regular magnitude, this would be square root of 2. Okay. Phase. So again, at the frequency of 0, that's way, way, way to the left. Phase is asymptotic as well. This is going to be a phase angle of 180 degrees. (400 megahertz to determine the phase. This is 100, 200, 300, 400. And so this would be a phase angle of approximately 100 degrees right off the chart. Okay, every so often it just does this where it just paint dripping. All right. 800, 100. Okay. Any questions about filling out this chart here? Okay. All right, so if we want to know then what is the voltage out, we just then fill this in, right? So we use this equation as kind of a template for filling this in, but we would say that the V naught, or V out, VO of T is equal then, okay, so it's equal to 2 times the amplitude of that signal coming in, so 2 times a half is 1, cosine 0t plus 180 degrees plus square root of 2 times the amplitude of the second one, which is 1, that's just square root of 2, cosine 2 pi times 400 times 10 to the 6 t plus 100 degrees. Okay. All right. Cosine of 180 degrees is what? -1, right? So it flips the sign. All right, so if I look at and say that, okay, what is the actual, if I simplify this, I have -1 plus square root of 2 cosine 2 pi times 400 times 10 to the 6 t plus 100. Okay, so walking through what this did and how this is not behaving like the ideal function. So the signal that was at 0 hertz, it performed in an ideal manner, right? So the purpose of this was to take a signal and you multiply it by -2. Right, so if we look at the DC component, it did exactly just that. Where is this at? So the input was 0.5, output is -1, right? So it did that perfectly. And then you get up to a certain frequency, and then this no longer behaves in an ideal fashion. You're above what's called the bandwidth of the system. So the system is designed to behave a certain way. We can't, any system, any physical system is going to have a trail off, and the magnitude is going to decrease with increasing frequency as we get to really, really high frequencies. So this op amp is very, very fast. 400 megahertz is extremely fast, but it's still not an ideal system. At that frequency, it starts to trail off. So you can directly see that in the Bode plot. And so this Bode plot gives you an idea of the operable range of this system. So we were at 400 megahertz, we're getting to be outside the operable range of the system. We're getting to be above a frequency where it will no longer perform that function very well, multiplying by -2. All right, and this is true of any physical system. Every physical system has limits, even really fast electrical devices. Okay. Right, any questions on that example? Sorry? Okay. So if you just connect normally without any modifications, this is going to give you -2. If you modify the resistors, it's going to give you, depends on your resistor values. Okay. But op amps, I don't know how many of your phones in your pocket right now. As electrical engineers, we don't use it, or sorry, as mechanical engineers, we don't use them all that often, but they are still valuable. Electrical engineers, they work in op amps essentially. Okay. Additional terms to know, DC gain. DC just corresponds to direct current. So we use the term DC gain that's borrowed from our electrical engineering friends. Basically, this is the magnitude of the frequency response plot in the low frequency region, provided that it is asymptotically going to a single value. So you'll see a lot of, especially with mechanical systems, you'll see a lot of magnitudes that have a -20 or -40 dB slope at low frequency. Those do not have a DC gain associated with them, but this op amp does. So the DC gain of this system is 6. So basically the flat low frequency region, DC gain is 6 for this example. Bandwidth. Bandwidth, you've probably heard on, television, they talk about AT&T as the best bandwidth. They're just using that term. That's not actually what they mean from engineering's point of view. So the bandwidth is basically the frequency at which the magnitude is equal to the DC gain minus 3 decibels. Okay, so in this example, we would go here and we say, all right, DC gain is 6. We go down 3 decibels. We see where that intersects the plot, and voila, we see that the bandwidth frequency was 400 megahertz. Okay. So the, yes? I'm saying that more for mechanical systems. For electrical systems, there's some discrepancy, but yeah. Again, but what's this say? Thank you. Students get 1 point for correcting errors in the notes. So, what's your name? Jackson. Sorry, what's your last name? Remus. Thank you. Okay. So bandwidth. These are always. It's always a frequency. So if you ever ask what the bandwidth of a system is, and you provide an answer of like 6 decibels or something like that, that's wrong. Bandwidths are always frequencies. So in this case, it's 400 megahertz, but the bandwidth is essentially the operable range of the system. So if we go up to this example, if we try and put in a signal of say 1 gigahertz or 1,000 megahertz, our output magnitude is going to be very, very small. So we'd have to carry this plot all the way farther down to look at what the gain would be, but it's going to get in the range of -6, -8 decibels or something like that. That's going to be attenuating that signal. So and as we try and increase the frequency of that signal even more, the gain is going to be even less. So we're having diminishing returns as we go up and up in frequency. So the bandwidth gives an idea of what range the system is operable. Where are we actually going to have a performance that is expected, or what it was designed to do. Yes?
So your phase diagram doesn't do the thing I'm used to where it kind of comes back in asymptotes and, like, I guess I think it's 0. Does it do that? It's just cut off?
It's cut off, yeah. Okay. Yeah. So it should be going from 180 to 0. Yeah. It's one, we have to go up 1 more decade. Why 3 decibels? Anyone know that answer? Yes?
Isn't that half? Isn't a gain of 3 decibels double the amplitude?
So it's square root of 2 over 2. So you're very close. Yes? Power, yeah. So power or energy can be computed by this integral equation here, right here. And so I'm not going to go through this, but basically if you're at an amplitude, or basically a gain of square root of 2 over 2, power is the signal squared, and so that becomes then 1/2 the power or 1/2 the energy. Okay, so it's completely arbitrary. Like, why is 1/2 the metric? I don't know. It isn't really, but it's a good, nice number that we can say, all right, if you get above the bandwidth, you're going to expect less than half of the energy or power out. If you're below the bandwidth, you should expect more than half of the energy or power out. Right? So it's artificially generated, but 1/2 seems like as good a number as any, right? In terms of power. So 3 decibels down is the bandwidth. Okay. This is above this, you get diminishing returns. Okay. Bode plots. I hope this is all very familiar to you. Just like you should have seen in 3260, we'll be plotting Bode plots by hand a lot in this class. The reason for this is not that we hate you and want you to do a bunch of meaningless work. Is at the very latter ends of this class, we're going to start to look at how we can use Bode plots to design systems. And so it is, from a pedagogical point of view, it's much better if you actually know how all these individual components add together. So we're actually going to be bending the Bode plot of integrated systems by basically putting poles and zeros in line with the system to make the Bode plot bend. And for you to understand how to do that, it's best if you go through the arduous process of doing it by hand. And so we will be doing that. Okay. So I'm just going to go through a really quick example of this. The main thing before we get into this example is to realize that a few basic points here is that we say we have some sort of transfer function. We evaluate this transfer function at I omega. That's how we always start Bode plots, right? We know that we can rewrite this Bode plot as this transfer function, or magnitude, not magnitude, the transfer function be rewritten as its magnitude and its phase. Okay, so this is the polar form of a complex number. Magnitude out front, phase in the exponent. Okay, so now if I have a transfer function that I can break up and say is composed of 3 individual terms like this, right? Then I can also rewrite g of I omega as 3 individual terms. So g of I omega, I could rewrite as g1, g2, g3, or I can rewrite this as magnitude of g1 I omega e to the I phase g1 of I omega, g2 of I omega magnitude, phase, and then G3. Okay, so these all combine, right? So I can always pull, these are just scalars up front, so I can combine these all together. So I get then that G of I omega is equal to magnitude G1, magnitude G2, magnitude G3, E, I, phase G1, plus phase G2, plus phase G3. Okay, so the main thing here is that the phases add. So phases add. Phases add, magnitudes multiply, but we are always using decibels when we plot Bode plots, and so that's a logarithmic transformation. And so we can use this property here that log of AB is equal to log A plus log B. And so if we express the magnitude in decibels, then our magnitudes add as well. So if I say G of I omega in decibels, this is equal to G1 in decibels plus G2 in decibels plus G3 decibels. Okay, so phases, in terms of Bode plots plotted in decibels, phases and magnitudes will both add. Okay, any questions on that? Okay. All right, so this is a lot of text. The main thing here for this example 3.8 is that we are going to be working with this transfer function. So just give an example of something that's in my lab, a system that we've identified a transfer function for. And so my student, or former student, he works for MathWorks now actually. So if you have any tech problems, call him. So this is a transfer function. The transfer function for this particular system is a robotic positioning system in my lab. He identified it to be 59.8 over s plus 4 as a simplified transfer function. So we're just going to use this as an example to go through and see if we can plot the Bode plot for this system. All right. So what we're going to do is we're going to realize that we can, if we want to get this in a simpler form, we can rewrite it as this right here. So I cut off the 14. So I personally like to pull, if you have a pole location, we have a pole location at -4 for this real pole. I find it easier to pull that out front, and so we get S, 1 over the quantity S over 4 plus 1. I find that easier to work with, and I'll talk about that why in a little bit. So that's going to change the amplitude of the system, but we have basically a gain on the system. We have a pole at the origin, all right, pole at 0. Oftentimes we'll call this a free integrator because remember, if you want to integrate in the frequency domain, you divide by S. All right, so you'll hear this as a free integrator sometimes. And then we have a real pole at -4 in our system. All right, so we can break this up into G1, G2, G3, plot each of these individual components, and then we can see what the entire plot looks like from that. Okay. All right, so first term is 14.94, right? So this is just just a gain, right? So G1 is 14.94. The magnitude of G1 is pretty simple. That's just equal to 14.94. If I want to know what is the magnitude in decibels, I have to do the transformation, and that is 23.5 decibels. Okay. Phase of G1. Okay, so if I look at the complex plane and plot, say this is the position 14.94. All right, I would see that the phase angle of a vector running from the origin to that point would be 0 degrees, right? It's going due east. So my question is, what would happen if my gain was negative 14.94? Where's the phase of a negative gain? I heard it somewhere up front. What was it? Anyone? Phase of a negative gain? 180 degrees. Yeah, so it's either 180 or negative 180. Either one works. So this would be a vector going from the origin to a negative number. That's 180 degrees. Okay. So that was a little aside. That's not actually part of the notes. Okay. So going back to the op-amp example, the purpose was to multiply by -2. That's why the low frequency phase was 180 degrees. There's a gain of -2. Okay, so we have this first component, magnitude 23.5 decibels, phase of 0. So going down to the region of the notes that has this Bode plot. So we'll use blank Bode plot paper pretty often in this class. If you want to get on Carmen, we have just a PDF of blank Bode plot paper if you want to print that off on your own. Sometimes that's helpful for certain problems. But so with each of these, though, we have to put axes on them. So -1, 0, 1, 2. Oh, what's a good color? Green. Okay, so the first component we hear with G1 is a magnitude 23.5. So and this is not dependent on frequency, right? So across the board, this could be 23.5. It has a phase angle of 0. Okay, so in terms of labeling this for your notes, this is magnitude, G1 in decibels, phase G1. Okay. All right. Next component is 1 over S. Okay, so standard substitution that we do is turn this into 1 over I omega. And if I want to get this in a little easier form to work with, I multiply top and bottom by I. Equals negative 1 over omega I. Okay, so if I want to plot this in the complex plane, the complex number negative 1 over omega I is due south. It's in along the negative imaginary axis. Say, for instance, it's this point. Over omega. So this is a vector going from the origin to this point due south, right? Okay, so the magnitude of G2 is going to be the length of that vector. One over omega. Phase of G2 is going to be what? Negative 90, right? So the phase angle of this vector here, okay, I'm having trouble seeing this. All right, phase angle of this vector, negative 90 degrees, right? And this is not dependent on frequency. It's always going to be negative 90 degrees. Okay. If we want to know what this magnitude, we have two things that we need to plot this. We need a slope and intercept. So slope is negative 20 dB per decade. This is coming from the fact that if we go up a decade, so if we increase by 10x, that means that magnitude, GT of I omega, is multiplied by 1 over 10, right? So slope is rise over run. Go up 1 decade, that's a factor of 10. Magnitude gets multiplied by a factor of 1 over 10. 1 over 10 is negative 20 decibels. All right, so this is going to have an intercept. So we go slope. Slope is negative 20 dB per decade. Intercept. We can plug in any number we want. The number that's probably most easy to work with is a frequency of 1 or 10 to the 0. So if I look at this magnitude, if I plug in 1 for frequency, magnitude is equal to 1. Or in decibels, that's a magnitude of 0, right? Doing the transformation. Any questions about the pure integrator or pole at the origin? Yes?
Earlier when you said, like, you did the aside and you said it was equal to 180.
Yes.
I thought, I misunderstood what
That was, the aside was just if, so our gain is 14.94, right? So the aside was, okay, what if the gain happened to be negative 14.94? It was just like a quick question to ask. So then if we look at the complex plane, 14.94 is along the positive real axis. Negative 14.94 is along the negative axis. Right? So just making sure students realize that if you ever see a negative gain, that should be automatically click as that's a 180 or negative 180 degree phase shift. Looking at kind of tying that into the homework problem, problem 1 that's due today, right? So one of the problems asks, what happens if you multiply by I, right? That's a positive 90 degree phase shift, right? Negative 1 would be multiplying by 2I, right? So that'd be plus 90, 180 degree phase shift, if that helps tie everything together. Okay, so these terms. We'll use a different color pen. We'll do purple. Okay, we'll do the phase first because that's the easiest. That we said was negative 90 for all frequencies. Okay. Magnitude, we have an intercept that is a frequency of 1 and a magnitude of 1, or 10 to the 0, and 0 decibels. And we know that the slope is going to be negative 20 dB per decade. So at each decade, we're going to go down 20 decibels. So I'm just going to connect these dots here. So this is the magnitude of G2. Okay, last term. Last term is the real pole at position negative 4. Okay, so I hope you're very familiar from plotting real poles from 3260. Basically, we're looking at asymptotic approximations of the real pole. The other two things I plotted so far were exact. These are just asymptotic. And what we look at is we look at frequencies much, much less than that pole location. Or look at a frequency exactly equal to that pole location and a frequency much, much greater than 4. And we're going to make statements about what is G of I omega in decibels, phase of G of I omega. Okay. So if I look at this transfer function, I plug in 1 over I omega. Okay, and if I look at the case of omega much, much less than 4, that I can just say, just call it 0, right? And I put a 0 in here and I get 1 over 1, okay, or 1. So the magnitude of 1 is 0 decibels. Phase angle of the number 1 is 0. If I plug in 4, all right, so I plug in 4, I get then the transfer function. So G3 of 4I is equal to 1 over I plus 1, right? So in terms of magnitude of G3, I get 1 over square root of 2, or negative 3 decibels. Phase angle, it's a quick little drawing here. Right? If I want to know where is I plus 1 on the complex plane, that is this vector. Right? So this has magnitude square root of 2, so that means that it's in the denominator, it's 1 over square root of 2. It's a phase angle of 45 degrees. That means the phase angle is negative 45 degrees. Okay, last one. Magnitude much greater than 4. Just throw in a really large number in here. What that means is we have to come up with some sort of asymptotic relationship for this really large number. Okay, so say for instance, I say that this is a really large number. What happens is that this 1 in the denominator no longer really matters at all, right? 1 compared to a really large number is meaningless. All right, so this G3 of I omega approximately goes to 1 over I in terms of anything that's important here. Okay, in terms of actual behavior. So sorry, that wasn't very clear. 1 over omega I. Okay, so omega becomes a really large number. This 1 is meaningless. We can just simplify this to be approximately 1 over I. Just like the pure integrator, this has a phase angle of negative 90 degrees as frequency gets really large. And it's also going to have a slope of negative 20 dB per decade. Okay. All right, any questions on that? Okay, so this means that magnitude, this goes in for low frequencies, 0 decibels, all the way up to a frequency of 4 radians per second. And then we're going to break down at negative 20 dB per decade from there on. Oops. Phase goes from 0 to negative 90. Because of the rule of thumb, the phase for a real pole takes 2 decades to go from 0 to negative 90, and it's centered around that pole location. So what I'm going to do is I'm going to mark 0.4, that's right there, and 40. Right here. So this phase for the real pole is going to go from 0 to negative 90 over the course of 2 decades. This is phase G3, magnitude G3 decibels. All right. All right, so now we just need to bring this all together. I would just recommend working from left to right on this. That's what I find to be the easiest way to do it. So if I look at low frequency regions for adding together the magnitudes, here's a nice point because these two plots intersect and they both intersect at 0. So if I look at adding all these terms together, this is going to be the plot for the total Bode plot. All right. It's going to have a slope of negative 20 dB per decade for a little bit. And then as soon as I hit 4 radians per second, it's going to transition from having a slope to negative 20 dB per decade to negative 40. So if I'm going to drop 40 dBs in 1 decade, that means by the time I get to 40 radians per second, oops, I was a little off here. This should be, I drew it to 50. Let's redo that. Times I get to 40 radians per second, now it's going to be at somewhere a little bit less than negative 20. Is that correct? Yes, okay. Okay, so this is a slope of negative 20. This is a slope of negative 40 in this region. Phase information, this negative 90 is pervasive, so basically all this does, it's 0 plus negative 90 to shift everything by negative 90, and then follow the contour of the phase from the real pole. So that's everything added up in both magnitude and phase. Any questions about that example? Okay. So the last 5 minutes or so, I just wanted to show some software tools for this. I think everyone should be hopefully pretty aware of the command Bode. So I can enter in a transfer function. So the base transfer function we started with was 59.8 over the quantity s times s plus 4. So I hope everyone is familiar with the TF function from 3260. But this would be our transfer function in MATLAB. If I want to get the Bode plot for this, I just do Bode G. Okay, so this is basically what we saw before. This is just the real Bode plot. So it's not asymptotic, it's not an approximation, but we can see the break at around 4 radians per second, et cetera, all these individual features that we saw right here. If you go to Carmen, you'll find that there is you'll see that there is a help. Let me find that actually. For some reason, anything that's OSU related is not working on my computer right now. Actually, where is this? Sorry, I should have this loaded up before. Yeah, crap. Okay. All right, so if you go to Carmen, there's this GUI called Bode plot GUI. This is something that someone else wrote. I didn't, but it's available for free. And so what it does above and beyond the Bode plot, the actual Bode plot, it gives you all the asymptotic approximations as well. Okay, so it helps if you want to check your work in terms of drawing these. It's a nice software tool to do that. We already have G in the workspace, so we can just go and say find user systems. We say G, and it's going to then plot a few things for us here. I can't seem to zoom in on this, but what you'll see here is it labels everything. So you have a pole at the origin that's given by this blue dotted line, real pole at -4, constant at 15. They kind of routed up there to 15, but these are all the elements that we chose to plot in our solution, and you can see these directly reflected on this plot. The thin black line here is the actual Bode plot, exact one, and you can see it with phase as well. The other things you can do is you can actually start to add and subtract, you start to subtract elements too. So we say, all right, what happens if you just want to check your understanding? What happens if I take out the real pole? How does that change the plot? And it'll change it automatically for us, so you can put it back in. It doesn't handle everything, so I think it's not the best GUI. I'll give it like a C+. I think it doesn't handle I forget what it is. It doesn't handle like zeros in the right half plane and time delays and stuff like that. So it's missing some features, but it has. If you just want to check your understanding, it's a good tool to just really quickly plug in a transfer function and see if you did it correctly. Okay. All right, with that, we are done with the review of 3260. Friday we'll start talking about electromechanical machines.